Hey everyone, it's Dr. Walker. Let's look at another example from v061C on angular momentum. In this example, we have a sphere of mass 1 and a block of mass 2 are connected by a light cord that passes over a pulley. The radius of the pulley is r and the mass of the thin rim is m. The spokes of the pulley have negligible mass. So what we're saying is that this pulley here can be approximated as a hoop or a hollow disc. The block slides on a frictionless horizontal surface. Find an expression for the linear acceleration of the two objects. Does this problem look familiar? Remember when we were working with Newton's second law and we had these types of problems? The only difference is that we neglected the size and shape and mass of the pulley. But in fact, it affects the motion, so here we get to take it into account. Let's take the angular momentum approach. Let's use Newton's second law for rotational motion. The net torque, the net external torque, is equal to the derivative with respect to time of the angular momentum. In order to use this equation, we have to solve for each of the two sides separately and then see what we get. Let's look at the net torque on the system. First of all, we have to define our system. Our system is going to be mass 1, mass 2, and a pulley, and the rope connecting them. That will be our system. So to find a net external torque, let's look at all of the forces that are possibly producing some torque. For instance, M2 has weight. Does that produce any torque about our axis of rotation, which is going to be through the center of the pulley? Well, it possibly could, but we have a normal force that is going to oppose it. So if M2 were to cause a clockwise torque, the normal force would oppose it. So we don't have to worry about the normal force or the weight of mass 2. What other forces are there? At the pulley, we know there's the weight of the pulley, and there's a normal force from the bearings. Those forces are going through the pivot, so we know they don't exert any torque either. Okay, what about the tension in the rope? Well, the pulley has a tension pulling it to the right here from the rope, but the mass 2 has a tension pulling it to the left. It's the same tension, same rope. So the torques from these two tensions cancel out. So does the torque from the two tensions over here. It turns out these tensions are internal forces. So we don't have to consider them when we're looking at the net external torques. So what's left? The only thing that's left is the weight of M1, so F1G. That's pulling down, that's causing this rotation, this unbalanced rotation. It's causing the whole thing to rotate counterclockwise. Let's find an expression for the net external torque. We can use F perpendicular R. In this case, the force is straight down, and the distance from the pivot to that force is R. It's the radius of the pulley. And they're perpendicular to each other. So we can just do the force times the distance to get the torque. The force is going to be the weight, so F1G, it's going to be M1G, and then the distance is just the radius of the pulley. So that's how we find a net external torque on the system. Now let's look at the angular momentum. And notice that I neglected the vector sign. It turns out that the torque and the angular momentum, they're all in the same direction. Do you remember how to find the direction of the torque? We can use our R cross F definition. Point your fingers of your right hand to the left in the direction of the R. Fold them down in the direction of the force. Your thumb points out of the page. So the direction of the torque is out of the page. Let's look at the angular momentum. The angular momentum of M1. It's a particle, so we can use the MVR definition because the speed of M1 is perpendicular to R, which is our position vector from the pivot to where that speed is. So R and V are perpendicular. We can use the MVR definition, M1 V R, to find the angular momentum. And what's the direction? Well, we can do r cross p or r cross v since p and v are in the same direction. Point your fingers to the left, fold them downward, your thumb is out of the page. So it's out of the page. Let's look at m2, its angular momentum. It's a particle, it's going to the left, and a position vector is going upward. So once again, they're perpendicular to each other. We can use the MVR definition. What's the direction? Point your fingers upward for the R, fold them to the left for V, thumb is out of the page. So we are paying attention to the direction. If there was an angular momentum going into the page, we could just subtract it. But here we can just find, this can be the magnitude of the torque, the magnitude of the angular momentum, because we are paying attention to direction. They're just all in the same direction, so we're just adding them. What about the angular momentum of the pulley? Let's look at that one on the side here. Angular momentum of the pulley. It's a rigid rotating object. We can use I omega definition for angular momentum. We said that it's going to be a hoop or hollow disk. Can you find the moment of inertia of a hollow disk? It's mr squared. Now we could leave our omega as omega. However, the other terms for angular momentum are in terms of v. We know that we can convert omega to v. If we consider a pulley here that has an angular speed omega, if we consider a point on the edge of the pulley here, it's moving with a linear speed v to the left. And that v is related to omega because omega is equal to v over r. So if we consider a point at the edge, which moves with a speed v, which is the same v as the rope and as the masses, then that point on the edge is a distance capital R from the pivot. So for omega, we can use v over r. So it turns out that the angular momentum of the pulley, after you cancel out an r, is mrv or mvr. It's the same expression as the angular momentum of the particles. This is only because the pulley happens to be a hollow disk. If it was a solid disk, we would get something different because the moment of inertia would have a factor of 1/2, for instance. But in our case, we have 3 MVRs that we are adding to find a total angular momentum. The direction of the angular momentum for the pulley is also out of the page. You can look at the direction of the angular speed, right? If you rotate your fingers in the direction of the rotation, you rotate your fingers counterclockwise, your thumb points out. That's the direction of omega, the omega vector. It's also the direction of the angular momentum vector because L and omega are in the same direction. So they're all out of the page. Now let's go ahead and take the derivative of our angular momentum. With respect to t. Now actually before we do that, we can go ahead and factor out all of the masses. Hopefully you have some room right here above this. Factor out the masses first. m1 plus m2 plus m times vr is our L. And now let's find the derivative with respect to time. The only variable that depends on time is the velocity. So the m's and the r are constants. We can take them out of the derivative. And then we just have dv dt left. And dv dt is just our linear acceleration. Thankfully, that's what we're looking for. So we're getting really close now. So the derivative of the angular momentum with respect to time is m1 plus m2 plus capital M times capital R times acceleration. Now we can put the two sides of Newton's second law together. The left side, the net torque, is m1gr. And then the right side is m1 plus m2 plus m times RA. Now we can solve for A. We can cross out the R and then divide by the sum of all the masses. We get that our linear acceleration is m1g divided by m1 plus m2 plus m. So we were able to use Newton's second law for rotational motion using the angular momentum approach and consider the system of the three objects and find their linear acceleration.